Welcome back, YouTube community. This is Philip Trinath. This video can be considered as an extension to the experiment in the previous video. The objectives of this presentation are first, basics of PPG signal, followed by implementing moving average filter on real-time PPG signal. Real-time PPG signal in the sense reading data from the PPG sensor, followed by implementing our algorithm on the signal. This is followed by implementing difference filter on real-time PPG signal, baseline drift extraction using moving average filter for again real-time PPG signal, and this will be followed by the analysis of the results. So let's get started. So in the previous experiment, we have looked on how different filters work with the recorded data. Now we will process real-time PPG signals. So firstly, what is PPG? PPG stands for photoplethysmography. PPG measures the volumetric change of heart by measuring light transmissions and reflections sent by the PPG light sensor. As the heart contracts, blood pressure within the left ventricle, the main pumping chamber actually, increases. So by simply sending a light on a patch of skin with an LED light source which is present on the PPG sensor, as you can see in this image, the increased pulse pressure will cause a measurable difference on the amount of light reflected back and transmitted into the skin through a light sensor. This will be measured using this PPG sensor, and data will be recorded using the various equipment present in the backside of the sensor. This will The LED light should be placed in the area where arteries are pretty close to the skin, and one best option is our fingertip. So as you can see, this is a typical PPG sensor. This is the front side and this is the back side. Front side has an LED which actually acts as a light sensor by sending the light and measuring the reflected light that that is reflected by our skin and which varies according to our pulse rate. Amplitude of this signal is directly proportional to pulse pressure. Higher the peak, obviously stronger the pulse. Each peak in the resulting signal can be identified by special heart rate algorithms. So initially we find out different peaks. Once we get the peaks, we find out the time between the peaks. And once we get the time, we can find out time between successive peaks. We can find out the heart rate. Thus, in this way, through the PPG signals, we get our pulses, our pulse rate, our pulse, and from the pulses, from the pulse waveform, we get the heart rate. So now moving on, we'll see how to implement moving average filter on real-time PPG signals. The code remains pretty much similar to what we have done previously. We need to incorporate small changes in order to record signals from the PPG sensor. So above part, all this part remains the same till here. We add a small piece of code here, that is pin mode A0, input. A0 is an analog port in Arduino Duo port, and we are taking that as input. So this command states that A0 analog pin is my input now. Now coming back, so this for loop collects the data from the PPG sensor. So now I am processing 500 samples, but the sensor gives me analog signals. I need to discretize it in a time domain. That is why I sample it using 100. I sample it for suppose say 100 hertz. So I put a delay of 10 milliseconds here, which is equivalent to 100 hertz. So why we need to do this is our processing is done in digital domain. We process it per fixed number of samples and input is a analog signal. That is why we discretize it in order to process it. So this is the code for, as you've already seen, this is the code for moving average filter. So now we plot this. We plot the input waveform and the moving average filter waveform. So my blue color signal is the moving input signal, that is real-time PPG signal obtained from the PPG sensor, and the red signal is moving average filter output. As you can see, although the noise is comparatively lesser in the inputs compared to the previously recorded data, still it is completely smoothened in these portions, as you can see. Thus, our moving average filter is working pretty good, fairly good for even real-time signals. So next, we'll see how we implement difference filters for moving average for PPG real-time PPG signals. So here also we add pin mode A0, and A0 is my input. We collect the samples here, collect the real-time data here, delay it by 10 milliseconds, that is sample it at 100 hertz frequency, and uh, what we do in difference filters is our basic operation here is to find out the peaks. Peak detection is our objective here. So as the original data has some noise in it, initially we smoothen it using moving average filter. My order is 8 here as usual. This will be followed by implementing difference filters. This is the code for difference filter of order 1, that is you can see here y of I minus y of I minus 1, and this is the code for difference filter of order 2, y of I minus y of I minus 2. So we are printing the same, or we print the smoothened waveform, difference filter of order 1 and 3-point central difference. This is a resultant waveform. Blue color signal is my input. As you can see, the red color signal is my moving difference filter of first order, and green signal is my difference filter of 3-point central difference. 3-point central difference actually emphasizes peaks little more than the difference filter of first order. As what happens in 3-point central differences, we take the difference of initial present input and second passed input. That will be my present output. So whenever there is a peak, the distance between peak and second passed output is more than the distance between peak and passed input, as you can see in this waveform. That is why uh, a derivative difference filter of 3-point central difference is emphasizing peaks more in this case. That is not the case every time, but at least in this case, that is what happening. So now we'll come to baseline drift extraction. The theory for baseline drift extraction can be found in my previous video. In this video, we'll see how to implement this on real-time signals. Here I'm collecting 100 samples for input. That is the first line of my code. And I'm using derivative moving average filters of order 8 and 800. So initially, uh, we are sampling and recording the signal and sampling it, followed by applying moving average filter of order 8, K1 is 8 for me, and this will be followed by applying moving average filter of order 800, K2 is 800, and followed by Y2 has my moving average filter of order 800. That means Y2 has the baseline drift component with it. I'm subtracting the Y2 from Y. Y is moving a smoothened waveform. That is the waveform obtained after passing through moving average filter. So my Z will have a pure original signal which is free from moving from baseline drift component and which is also smoothened. So I will be plotting the input signal Y2, that is baseline drift component, Z, which is the signal which is smoothened and free from baseline drift component. As you can see, blue is my input, red is my baseline drift component, and green is my final clean PPG signal. It is pretty clear that the baseline drift component here is almost a straight line, which means the data we have collected is uh, free from this low frequency noise, we can say, and thus our baseline drift components is almost a straight line. So once we have subtracted this from the smoothened waveform, the output remains pretty much same as moving average filter of order 8 output. This is the same thing where I've just increased the gap. There's a same waveform with different scales. So that was the end for PPG signals. Now we'll move on to ECG signals. ECG stands for electrocardiogram. So what algorithms remain exactly the same. So I'll be analyzing the results. So the specialty in ECG or the beauty of ECG is there are many spikes in the input signal. Blue waveforms are my inputs and red are my outputs. There are many spikes. So if we pass this through moving average filter for smoothing, and if the order is suppose high, suppose say 8, what happens is it averages the present input to past 8 values. So as you can see, if I average this with the past 8 values, it will be smoothened or flattened. So I can't retain this spike. So in order to retain this spike, what I need to do is reduce my order. And what my order should be, I'll get to know that through my experience. Here we have tried with various orders and found out that order 3 remains very good. It retains the spike as well as smoothens the signal. As you can see, there is a little noise component here which is smoothened here, and every spike is retained. So there is a trade-off here between smoothness and retaining of spikes, and we need to choose the best possible trade-off. So this is peak detection in in ECG signal, which is obtained by passing ECG signal through first moving average filter followed by derivative filter of order 1 and 3-point central difference. So this is baseline drift extraction. As you can see here, blue is my input waveform, red is my baseline drift component, and green is the signal free from baseline drift component. As you can see, even here the baseline drift component is almost a straight line, indicating that my recorded input is decent enough and free from baseline drift component. Now we'll try the same algorithm on a different ECG data set. We are doing this experiment on different data sets to emphasize on the order of the filter. So how we have to vary the order of the filter in order to smoothen the waveform as well as retain the characteristics of the waveform. So in this waveform, uh, there are peaks, but peaks are not as pronounced as in the previous waveform. So I have the liberty to increase the order here in order to smoothen the waveform. And as the peaks, number of peaks are not very high and not very sharp, I can retain them also. So my order here was 4. This is the input waveform and red is the output. As you can see, there is a lot of noise in the input waveform, but that is smoothened in the output and the peaks are also retained. This is peak detection, again using moving average filter followed by difference filters. And this is the baseline drift extraction. So that's it from my side. Thank you and stay tuned for our channels for more interesting videos. Thank you.